Okay, so let's talk about algebraic data types. Why is it an algebra? So we have products and we have sums. Just like in algebra, right? So we have multiplication. Product sort of like multiplication. What does it mean? What is multiplication? It means that we have a monoid, at least, right? So a monoid would be something that has multiplication, that's associative, and has a unit. But now we are talking about types. Is there something like an algebra of types? Is the product in the algebra, in types, actually behaving like multiplication? So let's check a few things, and we'll do this in Haskell, right? So first of all, the product of numbers, it's not true about any monoid, but the product of numbers is symmetric, usually. Let's see if a product of two types is symmetric. So if we have a product of two types, that's a pair of type A and B, right? Is it the same as a pair of B and A? And the answer is, no, it's not. If you have a function that takes a pair of A and B, like a pair of int and bool, it will not accept a pair of bool and int. It won't type check. So these two types are not the same. However, they contain exactly the same information, right? They just have it encoded slightly differently, but the information is the same. Which means that actually they are isomorphic. And the isomorphism between these two types is called swap. So there is a function, right, that takes a pair of AB and returns a pair of BA. And it's really easy to implement. Swap takes a pair and produces another pair in which the first element is the second of the pair and the second element is the first of the pair. Okay? So it is not symmetric really, but it is symmetric up to isomorphism. So this is not really necessary for me to show you that this is a monoid, because a monoid doesn't have to be symmetric, but it's just an interesting thing, right? And also we notice that there's this thing called up to isomorphism. So the next thing about a monoid is that a monoid product should be associative, right? So what does it mean associative in this case? It would mean that if I take a pair A and B and pair it with C, is it the same as pairing A with a pair of B and C? And again, the answer is no. If you have a function that takes this type, you cannot call it with an element of this type. It won't type check. But again, these two types contain the same information. It's rearranged. And this rearrangement can be written as an isomorphism, right? So I can write a function, called assoc with a name, right? So it will just A, B, C. I can pattern match it, right? And then I return a pair of A, B, C. Right? I'm pattern matching to extract A, B, and C, and then I can rearrange and pair B with C and then pair it with A. Right? Now, I said this is an isomorphism, right? It means it has an inverse. It must have an inverse in order to be isomorphism, right? Turns out swap has an inverse, which is swap. So if you swap twice, you get back the same thing. So swap really is an isomorphism. And so is assoc. It has an inverse. It's not its own inverse, but it has an inverse, right? So it is associative this multiplication of types is associative. Okay? Now there's one more thing, right? Does it have a unit of multiplication? Like, what would be the type that if you pair it with any other type, you will just get back the same type? Any ideas? Well, it has to be a type that has only one element, right? Because if I put something that has two elements, I'm just doubling the number of possible values, right? So, the type that has one element is called unit, right? So, again, this is not the same as A, right? But it is isomorphic to A. It has like exactly the same elements, right? So I can define this isomorphism in one, on one hand, I will say unit. Well, unit is not a good name, right? M unit, let's say, okay? M unit takes an A and returns an A, okay? So I can put an X here, right? So I do pattern matching on this. And vice versa. M unit inverse takes an X and produces X, comma unit. Right? And this is an inverse of each other. So these two types are isomorphic. This is like, taking a Cartesian product of a line with just a single point, right? You get the line again. So the trick is, that you can always form a pair. If you give me an element of A, right? If you give me an element of A, I can form a pair A and unit because I can always take a unit from thin air, right? And vice versa. If you give me a pair of A and unit, there's no more information there than just the first of it, right? So in fact, I could have called it, first. Or even this, right? Point free notation. But anyway, so this is right, and of course this is right unit, multiplication on the right. I could show you that it's left unit, but it's symmetric, modulo isomorphism. So modulo isomorphism, this is a monoid. Okay? So it's nice that there's this like little algebra here of where this really means multiplication, and in fact, I can write this as this weird notation. I can write it as A times 1 equals A, right? A times 1, where 1 stands for unit type, is the same as A. Where equals means really up to isomorphism. So we have like the standard algebra A times B, the standard monoid times C equals A times B times C. We have all these equations from school algebra. We can rewrite this. Okay. And the fact that it's associative, right, is very important because it means that up to isomorphism, it means that we can iterate these pairing, and in fact we can skip the parentheses and say, well, this is really the same as just a triple ABC, right? whether it's A paired with B and then with C, or the other way around, you know, it's the same as a triple ABC. So these tuples and of course structs or records with multiple fields and so on, they are just examples of this stuff, right? And we don't really parenthesize structs. We just say, you know, these are the elements of the struct because they are just tuples, just huge tuples. Okay, so this is this part of the algebra. A monoid with respect to product. Now what about sum, right? I said coproduct and either that's a sum type, right? So again, it is symmetric up to isomorphism. If you take either A and B, either A or B, I should say, right? That's isomorphic to either BA. And the isomorphism is you pattern match on left and right, and you return right and left, right? Not a big deal, right? Similarly, it's also associative up to isomorphism. So in fact, you know, if you want to associate a bunch of these ethers, you can as well write data structures like, you know, triple data triple ABC equals like left A or, okay, in Haskell we do this, or right C or middle B, right? So just putting these vertical bars means you have more options than just two, right? So it's like here we have tuples, here we have these multiple selections for our data. And we can pattern match on 3 constructors if we want, you know, and so on. So this is also, so this kind of follows from the fact that the sum is associative, that you can do stuff like this. Because up to isomorphism, it really doesn't matter in which order you order them. Now, final thing, right? We would like this to be a monoid again. What's the unit of sum? And that's a tricky one. Yes? Void. So either A or void. I'm saying this is isomorphic to A. Okay? So void is like 0. If either is like a plus, okay? So I'm saying that A plus 0 equals A. Okay? Why is that true? Like, what are the inhabitants of this ether? If you want to create an ether of A and void, right? You have 2 choices, right? Ether has 2 constructors, left and right. So if you give me an element of A, I can construct a left of A, and that's good, right? Are there any other inhabitants of this ether? Can I construct a right? I could construct a right if you gave me an element of void.
But you can't give me that.
But you can't, right? There are no elements of void. So you can never construct a right. So this sum really has nothing on the right. All the inhabitants of the sum are in one-to-one correspondent with A's, with inhabitants of A, with elements of A, right? So really, either A and void is the same as A, right? So it is a unit of sum. which normally is a zero, right? A unit of sum is called zero. So we have a zero. So we have two monoids, okay? But that's not all. Because we would like to combine these two monoids into a bigger thing, right? And what would be a bigger thing? Well, for instance, from algebra, we know that we can multiply by zero, right? We have this thing, a times 0 equals 0. Is this true? Okay, 0 is void. Times means product, pair. So, a pair of A and void. Is this void? Isomorphic to void? Well, can I construct a pair like this? How many inhabitants do I have? Well, you would have to give me an element of A and you would have to give me an element of void. Oops. Right? You can't. So I can never construct a pair of A and void. Therefore it's empty, uninhabited, which is the same as void. Okay? So A times 0 is also 0. What else do we know from algebra? Well, there's the final thing. It's distributive law, right? So A times B plus C, right? That should be A times B plus A times C. Is that true? You bet it's true. I mean, except it's up to isomorphism, right? But it just means that a pair, so A times means a pair. I don't know where I should write it. Maybe I can erase this part, okay? So we have a pair of A and either B or C. And this is the same as the sum, either a pair of AB or a pair of AC. Right? You see that it makes sense? Right? So if I want to form this pair, I have to have A or one of these guys, either B or C. Right? Or either left B or right C. Right? If I want to construct this, I either have a pair of AB or I have a pair of AC. But I just said the same thing, right? Just using different words. And of course I can write code that will pattern match on this, left, right, and then rearrange it into this one as a homework assignment, right? And you can show that this is really isomorphism, so there is an inverse function that does the opposite, and their combination will give you universe. So we have, what is this structure called when you have both multiplication and addition in the same thing? Well, in general, a structure like this is called a ring, okay? Except that ring, a true ring, also has an inverse of addition. That's how mathematicians define it, okay? And here we don't have inverses. Okay, this is one thing that we don't have. We don't know how to subtract. We can add things, right? Creating some type, but we don't know how to subtract something. Right? What's the inverse of integer as a type? There's nothing, right? And same with multiplication, with product. There is no inverse for product. So a ring that has no inverse is called a rig. It has a missing end.
Rig.
Or it's called semi-ring.
Without an inverse missing in radar.
Yeah, so it's ring without an end, without negative. It's called a ring. It's a pun to use in mathematics, right? Or semi-ring. Semi-ring is also maybe more often used name. Right? So types form this kind of interesting algebraic structure of a semi-ring. Okay, but well, let's do a few other things. Like, what is the correspondence of 2 equals 1 plus 1? Okay. Any guesses? So 1 is a unit type, right? So we have an either of unit or unit. So it's like there are only 2 possible values, left unit or right unit, right? We can call left unit true and right unit false. So 2 is a bool. Isomorphic, right? Right. What else? 1 plus a. 1 plus a is our friend maybe, right? Because maybe, I don't know if we have defined maybe before, but if we haven't, then we should, right? So maybe, data maybe, so this is data definition of maybe of A equals, it's either nothing or just A. So it has 2 constructors. One constructor which takes no arguments. So it's really equivalent to unit, right? Because you can just construct it out of nothing, literally, right? So this is equivalent to either unit. It's just we are giving this unit a name here. Instead of saying left unit, we say it's called nothing now. Okay, so we are just renaming left unit. We are calling it nothing. And A, right? So right A, we are just calling just A. Just a renaming of constructors, right?
Can you use arbitrary words for the constructors in the union?
Can I use arbitrary words for the constructors?
Right.
They have to be capitalized. But other than that,
it could be like
yes.
Bartosz.
Yes.
Okay.
Yes. Right. So the Haskell thing. Types have to be capitalized. Type variables are lowercase, but types, concrete types, are uppercase, and type constructors are uppercase.
But they could be anywhere else.
Can be anywhere. Yeah. It's just traditionally this is called left and right for the either type. Right? That's how either is defined. Okay. So we have these algebraic tricks. But there is one more interesting trick. Like when we have algebra, right? I mean, algebra really starts when you start solving equations, right? All right. Let's solve some equations.
Bring it.
So the equation that I want to solve is this. It's called L of, I'll write it as, in algebraic form. And I'll rewrite it as, so this will be L of x equals 1 plus, well, let's call it A. Because I want to translate it. Okay. So this is an equation for L of A. So we have a function L of A, right? that's defined as 1 plus a times L of a. So it's kind of recursively defined, right? Well, it's an equation for a function, right? How do we solve this? Well, we can solve it by like, let's put this on the left-hand side. So L of a minus a times L of a is 1, right? We can take L of a in front and say 1 minus a is 1, okay? I'm just doing this very trivial algebra. So this is 1 over 1 minus a. Okay? So let's translate this into types. Okay? And we'll see what the problem is immediately, right? So there's division and there's subtraction. but let's just be stupid. Okay? so I'll say data, and I'll call this a list, okay? List of A. Okay? Now the 1, that's just a unit thing. So there is a sum. So I will have 2 constructors, right? 2 constructors. This is a unit type, so it's just a constructor that takes no argument. I'll call it what? Null, nil, nil. Okay. Plus, and the second constructor I will call cons, and it's a product type, so it takes 2 things. It's a product of A and a list of A. Okay? Recognize this? So a list of A is either empty or it's a cons of a head and tail. Now this constructor takes 2 types as arguments. That's a product constructor, right? This is a sum constructor. So, and this is a constructor that takes no arguments, so it corresponds to the unit type. So this is like 1-to-1 correspondence between this equation and this. Now, unfortunately, I cannot do the division or the subtraction, okay? So, let me do a little sleight of hand, okay? Does anybody recognize this from, yeah? Yes? What is this?
If the absolute value of A is less than 1, you can find a geometric sequence.
It's a geometric sequence, right? Yes, it's a sum of a geometric sequence. It's not always convertible, right? But if its absolute value is less than 1, then Q? Yeah, exactly. So for n equals 0 to infinity, A to the power of n, right? Now this guy is good. This is only a sum, and these are products. This is A times A times A times A, and so on, right? So I could really rewrite it as, you know, for n equals 0, this is just 1 plus A cross A plus A times A times A plus, and so on. Instead of writing powers, I'm just writing this, right? Aha! So I could do this here, and I can say, okay, this corresponds to an empty list. This is just a singleton list. This is a list of 2 elements. This is a list of 3 elements. This is a list of 4 elements, and so on. I have defined all possible lists, right? With this equation. Right? Now this is a trick, right? What is not a trick, or is a little trick that can actually be explained later if we get to like things like initial algebras and so on, is that this equation can be solved by substitution. So if I take the, well, maybe it's easier in this notation, right? But in this notation I could say, or I can, yeah, So let me substitute for L of A. I will substitute the whole thing. So I have L of A equals 1 plus A times, and for L of A, I'm substituting this whole thing. So it is 1 plus A times L of A, right? Which is 1 plus, now can I do this multiplication of a sum? Right? I showed you that actually I can go with multiplication under the sum. So I can say A times 1. Oh, but A times 1, that's A, right? This whole algebra works on types as well, so I don't have to worry, right? And here I will do the substitution again, right? So I would say A times, and L of A is 1 plus.
Wait, you missed an A.
I missed an A, yes.
You got excited about the 1.
A times A
There you go.
times 1 plus A times L of A, right? And yeah, did I?
Yeah, that's right.
Yeah, that's right, right? So I can skip some of the parentheses because of associativity, right? So all this stuff, associativity, and I can just continue expanding this, right? And this expansion ends in a fixed point. The fixed point is this infinite sum, 1 plus A squared plus A cubed plus. So this is a way of obtaining the same thing without doing the power series, just doing this substitution and just finding a fixed point for this data type. And this can be formalized in a fixed point combinator and actually show that this actually gives the correct result. So this is how you get a list. This whole algebra is so nicely working. So this is why these are called algebraic data types. If you've heard the name algebraic data types before and you were wondering why are they called this, that's because of this stuff. Because it's high school algebra. And maybe not next time, but we will get to this point in which we actually do exponentials as well. So this algebra, we have addition, multiplication, will have exponentials as well. Okay, so then our algebra will be really, really interesting. And it's algebra on types. Okay, thank you.